Hello, good afternoon. Good afternoon, boys and girls. Clearance, please. Okay. Am I audible and visible? Can we start the class? Good evening, Garg, Govind Garg. सभी clear है? Audibility, visibility, clearance. Can we start the session? Okay, thank you, Siddhi Rathod. So very good afternoon to all of you. Welcome to Unacademy. Dr. Khalil Khan here. Operating System Course, नया आगाज सीरीज और हमारा टॉपिक चल रहा है मेमोरी मैनेजमेंट. इन द लास्ट सेशन हमने देखा कंटीग्यूअस एलोकेशन, जहां पर हमने बात की फिक्स पार्टीशन, वेरिएबल पार्टीशन की. और बच्चों आज स्टार्ट करेंगे नॉन कॉन्टिग्यूअस एलोकेशन. जैसे मैंने कहा पिछले सेशन में, वन ऑफ द बेसिक रीजन फॉर गोइंग इन फॉर नॉन कॉन्टिग्यूअस एलोकेशन इज टू ओवरकम और प्रिवेंट द प्रॉब्लम ऑफ एक्सटर्नल फ्रैगमेंटेशन. एक्सटर्नल फ्रैगमेंटेशन वुड अराइज इन वेरिएबल पार्टीशंस, particularly जब आपके पास free holes हो in between the partitions, in between the areas where program is present, then external fragmentation will arise. One of the solution हमने कहा for external fragmentation is go for defragmentation, जिसका नाम है compaction. But compaction is not a desirable solution due to the fact that it is a time consuming operation, and moreover it requires programs to support runtime address binding. So therefore the natural and obvious solution for a external fragmentation is to go for non-contiguous allocation. Non-contiguous allocation का basic paradigm ये है कि program can be non-contiguously placed in different areas of memory. ये requirement ज़रूरी नहीं है कि the whole program should be at one place. You can divide the program into modules, maybe pages, maybe segments, maybe other things. And then wherever free space is available, you can store the program. That is a basic notion, basic objective of a basic paradigm of non-contiguous allocation. So to study the non-contiguous allocation paradigms, what I suggest is we should basically start first the concept of address space. क्योंकि सभी non-contiguous allocation technique में we start the discussion with the non-contiguous allocation. So it is essential to really understand what is the meaning of address space. By definition, अगर आप पूछो, address space is nothing but a set of words, group of words, set or group of words associated with addresses. यह है basic definition of address space. Group of words, set of words. So that's why space का मतलब जब हम यहाँ पे ले रहे हैं, space is nothing but a group of words. तो जो space की बात हम यहाँ कर रहे हैं, it refers to space. Group of words, set of words, space of words. Words associated with addresses is called address space. और जो address होगा, that is unique word address होगा and fixed length address. If first word is addressed with 10 bits, every word will be addressed with 10 bits. So this is the ideology of address space. So essentially, जब non-contiguous allocation की बात होगी, there are two types of address spaces that we talk about. One is called physical address space. ठीक है? Address space को will write in short as AS. So therefore, physical address space will write in short as PAS. PAS. And the other is logical address space. we'll write in short as LAS. Conceptually, without losing any generality, you can say logical address space also same as virtual address space, because logical address is same as virtual address. So VS or LAS. लेकिन अंडरस्टैंड करना यहाँ पर यह है कि व्हाट एग्जैक्टली इज लॉजिकल एड्रेस स्पेस, व्हाट एग्जैक्टली इज फिजिकल एड्रेस स्पेस, एंड व्हाट इज द रिलेशनशिप बिटवीन देम, एंड हाउ दैट इज गोइंग टू प्ले रोल इन द डिजाइन ऑफ ए नॉन कंटीन्यूअस एलोकेशन टेक्निक, ये हमें स्टडी करना है. तो फर्स्ट वील बिल्ड अप अंडरस्टैंडिंग विथ रिगार्ड टू लॉजिकल एड्रेस स्पेस. व्हाट इज लॉजिकल एड्रेस एंड लॉजिकल एड्रेस स्पेस? So first we'll understand this. So suppose, for example, if this is the processor, and when I run any program on CPU, this is a CPU, when I run any program, the address generated by the program running on CPU, or we may say the address generated by the processor, जो भी processor address generate करेगा for accessing its instruction or data, ये address generate क्यों कर रहे हैं? For accessing the instruction or data that we want to execute. So the address seen by the program running on CPU, the address generated by the program running on CPU is what is termed as logical address. Logical address. We write in short LA. Naturally, the size of this logical address depends on the address bus supported by the processor. अगर आप मान के चलो कि size of the address bus is n bits, size of the address bus is n bits, then logical address will be of size n bits. Then based on this n bits of address, आपको पता है how many addresses are possible, the total number of addresses possible, arrangements possible, total number of addresses. Maximum possible is 2 power n. This is what you can call maximum logical address space. That means program can refer to maximum of these number of instructions or data units. Maximum. Actual can be slightly less. Actual can be much less, actual may be half, actual may be 1/4, but these are maximum that we can have. So the length of logical address is n bits and the corresponding logical address space is 2 power n. मतलब program जब run कर रहा है, ये वो मान के चल रहा है कि मेरा जो instruction है, जो data access है, जो data मुझे access करना है, that is having this address. But actually the instruction or data is present in memory, physical memory. So that means for every logical address generated, we should have its corresponding physical address. We should have corresponding. Why the program cannot generate the physical address directly? ये question आएगा आपके mind में. Why we can't generate? Because of protection. Multi-program environment में we have to protect the memory, because memory is one shared memory for all the users, all the processes. So if I allow the process to access physical address or physical address space directly, physical memory directly, protection violations may happen, right? Program may try to interfere with other address space, other program area. To protect that, this model, this concept is followed. Okay, running program will generate a logical address, virtual address, and we should basically have a mechanism by way of which we convert that logical address to physical address. That process of conversion is what is termed as address translation. Address translation. So diagrammatically, अगर आप समझने की कोशिश करो, so here I have physical address space. Physical memory कहिए आप, physical memory, main memory, where I have the physical address space of the program. So here I have actual program instructions or data unit. I am writing instruction or data unit, and the corresponding address needed to access this is physical address 1, physical address 2, something like this. So for this generated logical address, we should get the corresponding physical address. That process is called address translation. So who is going to do that address translation? हमने पढ़ा पहले के टॉपिक्स में हमने देखा था that conversion is carried out by a unit supported by memory system that is called MMU, memory management unit. We have already seen this. So MMU stands for memory management unit, memory management unit. The basic job of memory management unit is to take generated logical address as input and give the corresponding physical address as output. Corresponding physical address as output. The basic objective of MMU is to convert the generated logical address to its corresponding physical address. So this process, as I said, is what is termed as address translation. इसका नाम है address translation. So this approach is followed for the purpose of protection. Protection के लिए ये approach follow होता है. And study of every non-contiguous allocation policy from this architecture, we say, is based on 3 steps. So based on this architecture, we say it is 3 steps. Step one is organization of logical address space. Organization of this logical address space. Step 1. Step 2 is organization of physical address space. How is this physical address space organized? How is the logical address space organized? And third step is organization of virtual address, memory management unit. How this memory management unit is organized. So corresponding to generated logical address, we say we have a corresponding logical address space. Logical address space, also called virtual address space. So how is this organized? How is this organized? How is memory management unit organized? So study of any non-contiguous allocation technique like paging, segmentation, demand paging, inverted paging, multi-level paging, जो भी type of non-contiguous allocation technique की बात करो, from this diagram you should understand it involves 3 steps. Or tomorrow, for example, I used to say, if you design and develop your own non-contiguous allocation technique, then it should address these 3 steps. Step 1, organization of virtual or logical address space. Step 2, organization of physical address space. Step 3, organization of memory management unit. ये 3 step में हमें study करना पड़ेगा any non-contiguous allocation technique. So how do we study that in different techniques? So once again I re-emphasize, address generated by the program running on CPU is logical or virtual address, and corresponding to this logical or virtual address I will have a corresponding physical address. So set of all logical or addresses generated by CPU is termed as logical address space, and the corresponding physical addresses of those logical addresses is called physical address space. The maximum size of logical address space is 2 power n, where n is the size of address bus of the processor, and the maximum size of physical address space of the process is equal to the size of physical memory possible or available. ये है basic approach or basic design philosophy of LA and LS, PA and PS. Then finally, I would like to say the relation between logical address space, physical address and physical address space. Suppose, for example, the length of logical address is 12 bits. Example कह रहा हूं मैं. Then corresponding logical address space maximum that you can have is 2 power 12, 4 KB. And for example, its physical address is, let us say, 10 bits. And the corresponding physical address space you can have is 2 power 10, 1024 bytes, which is 1 KB. So therefore, as a generalized concept, what you can say is, if I say length of logical address space, size of logical address space or virtual address space is nothing but 2 power LA, and LA from here is nothing but log of LAS or VS to base 2. So this is the first conceptualization that you should have with regard to non-contiguous allocation. And secondly, corresponding to physical address space. So physical address space will be nothing but 2 power PA, and PA from here will be nothing but log of PAS to base 2. So this is in bits always. So this is the paradigm formulas, essential formulas for design of this. Okay. So based on this discussion, I will start my topic by name. Simple paging. Okay, simple paging. This is coming as R, but it is E. Let us mark it as E, simple paging. The study of the first non-contiguous allocation technique begins with simple paging technique. इसे understand करने के लिए एक hypothetical data set we'll take a hypothetical data set. Imagine that my system support a logical address space of 8 KB and a corresponding physical address space is 4 KB. Hypothetical data. That means the program running on CPU, आप imagine कर सकते हो, it cannot be more than 8 KB. But actual physical address space available for the program is only 4 KB. तो हम यहाँ पर देखेंगे कि how do we convert the logical address to physical address and access the instruction or data unit. So point number 1, for this logical address space, the corresponding logical address, you know, log of it, this is 13 bits. And log of this is physical address 12 bits. So हमें ये learn करना है, हमें ये देखना है कि how are we going to convert the 13-bit address to 12-bit address using memory management unit with simple paging technique. तो मैंने जैसे कहा कि first we need to address कि how are we going to organize our logical address space. So पहले हम यहाँ पर लिखेंगे title organization of logical address space. First I will tell diagrammatically, फिर उसके बाद मैं formulas लिखूंगा so that you can have attention, you can follow it carefully. Check. So imagine this is my logical address space of 8 KB. Let's write here the logical address space of 8 KB. So at the outset we say that the logical address space of size 8 KB will be divided into equal size units called pages. Equal size units called pages. These are the pages you can imagine. Like for example, in our case, let's say page size. एक page size हमें assume करना पड़ेगा. Let us imagine some page size. Page size could be हो सकता है like a power of 2, for example, like a power of 2. Let's assume in our case, in our example, let's assume, let's write it here. Let's say, let page size is equal to 1 KB. We are dividing the virtual address space or logical address space into units, into modules, chunks, which are called pages, with a page size of 1 KB. Generally, page size जो है 1 power of 2 रहेगा, 2 power something. Like 1 KB is 2 power 10. So it can be 2 power 10, it can be 2 power 11, it can be 2 power 12, it can be 2 power 8, it can be anything like a power of 2. So let page size be 1 KB. तो मतलब ये है कि हमारी entire address space 8 KB we are going to divide into pages of size 1 KB. तो कितने pages बनेंगे? 8 pages बनेंगे, and we are going to represent the pages with some numbers like this: P0, P1, P2, P3, P4, P5, P6, P7. So each page of size 1 KB. Each page of size 1 KB. So 8 pages. तो यहां पर हमारा पहला फॉर्मूला बनेगा बच्चों, लिखिएगा प्लीज, देखिएगा गौर से. नंबर ऑफ पेजेस in the logical address space, let us indicate by n, number of pages, is equal to given by logical address space divided by page size. ये हमारा फर्स्ट फार्मूला है. This is our first formula. Number of pages is given by logical address space divided by page size. 8 KB divided by 1 KB. I got 8 pages, P0 to P7. देखिएगा हर पेज का एक नंबर है, पेज नंबर, पेज आईडी 0, 1, 2, 3. तो this पेज नंबर बेसिकली डिपेंड्स ऑन नंबर ऑफ पेजेस. हर एक पेज को हम एक पेज नंबर से रेफर करेंगे. वी आर गोना रेफर एवरी पेज विद द पेज नंबर, पेज आईडी P0, P1, P2, P3, P4, P5, P6, P7. So that is called page number. So we have got 8 pages. To select one of the 8 pages, एक पेज को select करने के लिए out of 8 pages, how many bits of address is needed? How many bits of ID is needed? 3 bits. 8 can be referred with 3 bits. 2 power 3 is 8. So that is called page number. That is called page number. So यहाँ पे लिखेंगे formula for page number. We denote page number by P. So that depends on what? Log of number of pages. Log of number of pages is capital N to base 2. Page number. I have 8 pages. I need 3 bits. 3 bits can refer 8 pages. 2 power 3. So alternatively, the formula from here can be written like this. From this, I can say that capital N is equal to 2 power P. So therefore, this is my second important formula in the design of paging. Second important formula. Page number. Page number. ठीक है? So number of pages and page number. Now the addressing in logical address space follow 2 level addressing. जब कोई भी आप कंटेंट को एक्सेस करना हो पेज से, इंस्ट्रक्शन या डेटा रेफर करना हो, the addressing is two level addressing. मतलब first we refer a page, फिर page refer करने के बाद we need to select a byte or word within the page. That is called page offset or page displacement. जैसे कि I used to tell, अगर क्लास में we have students, there are benches, और मुझे कोई स्टूडेंट का नाम पता ना हो, रोल नंबर पता ना हो, तो हाउ डू आई एड्रेस द स्टूडेंट? आई कैन फॉलो दिस टाइप ऑफ टू लेवल एड्रेसिंग. मैं कहूंगा बेंच नंबर 14, student number 3. So bench number 14 is like selecting a page. Student number 3 is like selecting a word within the page, byte within the page. That is called page offset. So that is two level addressing. So I follow the two level addressing concept. So from here I say page offset, page displacement, page offset, also called page displacement, is given by log of page size to base 2. Because offset is measured in bits, so page size, PS is page size, right? So like in our example, page size is 1 KB. Page size is 1 KB. तो हमें कितने bits लगेंगे as a page offset? 10 bits लगेंगे. 10 bits. So page size is 1 KB, page offset will be 10 bits. 10 bits. So alternatively, the value of page size will be how much? The value of page size will be 2 power d. This is generally measured in bytes. This is generally measured in bits. So this is the third formula. In the study of paging technique, this is the third formula. So फिर से एक बार repeat कर रहा हूं. The logical or virtual address space is divided into equal size units called pages. Every page is associated with a page ID or page number starting from 0, 0, 1, 2, 3, 4. So if I have 8 pages, I need 3 bits, that is called page number. This is a formula for number of pages, formula for page number, formula for page offset. These are the three important formulas in the design of organization of virtual address space or logical address space in paging. And from here I say that the logical address format to be followed for paging system is having two parts. One is called page number, the other is offset. So this is the final format. This is logical address format. This is logical address format. Logical address format. Like for example, हमारे जो example हमने लिया है, virtual address space or logical address space is 8 KB, so therefore logical address is 13 bits. And page size is 1 KB. So I got 8 pages. So page number will be 3 bits. With 3 bits, I can select one of the 8 pages. Or the selected page is of size 1 KB. So how many bits of offset? 10 bits of offset. So 3 plus 10 total make 13 bits. So this is the organization of logical or virtual address space. Okay? So these are the conceptual formulas that you have to understand and remember in order for problem solving. जब तक आप ये अंडरस्टैंड ना करोगे प्रॉब्लम सॉल्विंग नहीं कर सकते. Okay, this is the first part, first step. So first step is here I'm writing organization of, here I have already written organization of logical address space. Now we'll go for second step, organization of physical address space. How is physical address space organized? So let's see here. So let me write second step, organization of physical address space. How is physical address space organized, conceptualized in paging technique? So understand करेंगे from the previous example. Our physical address space is of size 4 KB like this. So this physical address space of size 4 KB. So here I am writing first point with regard to physical address space organization. Physical address space is divided into units known as frames, and some people call page frames, and some people even call it as blocks, frames, with the convention that ये convention है, page size, frame size is always same as page size. Frame size is equal to page size. Why is this so? Because one frame can hold one page of logical memory. One frame can hold one page of logical memory. So इसीलिए frame size is same as page size. So in our example, page size is 1 KB, so frame size will also be 1 KB. So we are going to divide the physical address space into units called frames. So this is the first frame, like this, 4 frames. Like pages are given number, frames are also given number starting from 0. This frame 0, frame 1, frame 2, frame 3. So one frame can hold one page. So therefore this size is 1 KB exactly, because page size is 1 KB. Boys and girls, it is a frame to hold the page. जैसे I used to say photo frame. अगर आप एक frame लगा रहे हो दीवार पर, wall पर, photo frame, the size of the frame and the size of the photograph will be same. Then only it is meaningful. Otherwise कोई meaning convey नहीं करेगा. You cannot take a big frame, beautiful frame, and put a passport size photograph and hang it. That's not correct. So photo frame, उसी तरह page frame. A frame to hold the page. चूंकि नॉन कंटिन्यूअस allocation है, इसलिए any frame, any page can be kept in any frame. So let me write the next point. Because it is non-contiguous, any page can be stored in any frame, because this is non-contiguous. I have totally 8 pages in my logical memory. Here I have only 4 frames. So that means out of 8 pages, I can bring and load any of the 4 frames, any of the 4 pages. So let us imagine without any problem, I have some page number 5 here, I have some page number 7 here, I have page number 0 here, I have page number 2 here, something like this. So look at this, out of 8 pages, 4 of them I have loaded in memory like this. 4 of them. So now based on this, I can project the formulas. How do I write the formulas now for this? So again, I write number of frames first. Number of frames, let us denote by M, right? Or M dash will put is equal to the size of physical address space divided by page size or frame size. Frame number, let us denote it by F, measured in bits. I have got like page number, I have frame number. So there are 4 frames. So I need 2 bits to refer one of them. जैसा कि 4 pages अगर होते तो 2 bits होता. 4 frames है, 2 bits of address is needed. So therefore, the formula for number of frames is log of M dash. What is M dash? Number of frames, bits. ठीक है? And finally, the page offset and frame offset are essentially same, because page size is same as frame size. So page offset is equal to frame offset is equal to D. And from this I can say the format of the physical address का जो format है, 2-level format, it will have F and D. So boys and girls, these are the formulas. The first formula, second formula, and this is the third formula, final formula. So this is called physical address format. ये formulas अगर आप conceptually remember करोगे तो damn sure you will never go wrong in any of the problems. Recollect. These are the formulas: number of pages, page number, page offset. ठीक है? Here number of frames, frame number, and frame offset, and physical address format. So when I say number of frames are this, M dash value will be from here 2 power F. Number of frames is equal to 2 power 2 bits, 4 frames for our example. So this is the second step, organization of physical address space. So this was the first step, organization of logical address space, organization of physical address space. I will address your problem, Sidhu. Okay, have some patience. Just after completing the topic, I will take up your question. Okay. Next, we need to study the next step. That is the next step in the organization. Let us call it as organization of MMU, Memory Management Unit. The memory management unit in paging is known as page table. I write in short PT. Some people even also call it as page map table, page translation table, page map table, whatever. ठीक है. So थोड़े पॉइंट्स लिखूंगा आपके कन्वीनियंस के लिए. Each process will have its own page table. हर प्रोसेस की अपनी ओन पेज टेबल होगी. एंड पेज टेबल्स आर स्टोर्ड इन मेमोरी, फिजिकल मेमोरी, पीएम, फिजिकल मेमोरी. हाउ आर पेज टेबल्स ऑर्गेनाइज्ड? पेज टेबल्स आर ऑर्गेनाइज्ड as set of entries or words known as page table entries. We write page table entry in short as PT. Page table entries contain the frame number F of the page it is stored in. So जैसे कि for our example, if I try to have the page table here, let's say this is our page table. So as part of the design of the page table, I said each process will have its own page table. Number of entries, and page table is organized as series of entries, number of entries, where the number of entries is equal to number of pages. Number of entries is equal to number of pages. So here I have, for example, 8 pages, so I will have 8 entries, something like this. So this organization is very important. So here let's write, this is called page table, PT. Number of entries equal to number of pages. Yes, Prashant, every time page table has to be in main memory. The whole page table should be in main memory. अगर आप स्टोर नहीं कर पा रहे हो तो तभी आपको मल्टी लेवल पेजिंग के लिए जाना पड़ेगा. तो सुनिएगा प्लीज. So these entry for page number 0, page number 1, because every page will have its entry. So these are page numbers P. And this what is called page table entry. ये page table entry. Let's say size is E. Size measured in bits or bytes. Size is E. Page table entry. What does page table entry contain? Page table entry contain the frame number in which the referred page is present. Frame number. अब यहां से देखेंगे correlation. This mapping is important, boys and girls. अब देखिएगा page 0 is present in frame number 2. Page 0 physical page present in frame number 2. यही कुछ हम यहाँ पे लिखेंगे. Page 0. Where is it present? It is present in frame number 2, F2. Actually, frame number 2 in our example is represented with 2 bits. There are 4 frames, I need 2 bits. There are 4 frames, I need 2 bits. So this 2 in binary I can write like 1 0. Up next, page 1 is it present? No sir, it is not present. Page 2 हाँ sir present है. कहाँ पर है? Frame 3. यही यहाँ पे लिखेंगे. So 1 is not present. Page number 2 is frame number 3. So frame number 3, right? Page 2, look at that. Page 2 is present in frame number 3. So frame 3 in binary is 1 1, 2 bits. उसी तरह page number 3 not present, 4 not present, 5 is present in frame 0. 3 and 4 not present, 5 in frame 0. 0 is 0 0. 6 is not present. 7 is present in frame 1. 6 is not present. 7 is present in frame 1, 0 1. ये हम ऐसे ऑर्गेनाइज करेंगे पेज टेबल. So point number 1, number of entries in page table equal to number of pages. मैं थोड़ी देर में आपको बताऊंगा why it should be equal to number of pages. Why not it can be less. Secondly, page table entry correspond to the frame number. Page table entry contain frame number in which the referred page is present, so that we can get the translation information. Now using this, how do we convert the logical address to physical address? मैं यहाँ पर explain करूंगा. Please follow carefully. right? So I will say this is a CPU. This is CPU. Where any process runs on the CPU, it will generate a logical address. Logical address in our example is 13 bits. So this will be divided into P and D. The value of P is 3, the value of D is 10. Why 3? I have 8 pages, so I need 3 bits of page number. Page offset is 1 KB, so 1 KB need 10 bits. So because the process runs on CPU, generate an address having 3-bit page number. 3-bit page number के साथ process can refer to any of the pages, any of the 8 pages, 2 power 3. So that's why I need to have one entry per page so that it can resolve the address, it can resolve the reference. So for example, if this with 3-bit page number correspond to page number 5 like this, 101. अगर 3-bit की value 101, 101 क्या है? 5. Yes, that's correct, Sidhu. So with 3-bit page number 101, I refer page number 5. Page number 5 is present in which frame? Present in frame number 0. So I will take out this frame number 0. I will take out this frame number, which is how many bits? 2 bits. This frame contain the page. और पेज का ऑफसेट क्या है? टू रीड वन वर्ड और वन बाइट फ्रॉम द पेज ऑफसेट इज 10 बिट्स. कहां पर है 10 बिट्स? इन द लॉजिकल एड्रेस. सो आई टेक आउट दिस 10 बिट्स ऑफसेट डी. दिस इज माय फिजिकल एड्रेस of size 12 bits, and using this physical address I access physical address space, that is physical memory, for my instruction or data. ये access के लिए है? For your instruction or data unit, for your instruction or data. So therefore, by means of this diagram, I say that we have converted the generated logical address of 13 bits into 12-bit address using memory management unit called page table. ये है basic philosophy, basic ideology of simple paging technique that become the foundation for all other types of paging, including demand paging in virtual memory. ये काफी कुछ ज्यादा important है from GATE exam perspective. GATE exam perspective से काफी ज्यादा important है. Page table जो memory में store होगा, तो that will have its base address. इसका भी जो base address होगा page table का, this page table का base address will be stored in a table, in a register which is by name PTBR. इसका जो बेस एड्रेस है, like imagine for example the base address of the page table is some x, so this x will be stored here, PTBR, and this PTBR content or value will be kept in process control block. Process control block में PTBR की value store होगी. So every process का अपना own PCB होगा and PTBR का value होगी PCB में, and that will through that you can be able to access the page table. So this is the basic ideology. कुछ points यहाँ पे देखेंगे for your ready notes. The technique of mapping CPU generated logical address to physical address is called paging. Logical address space is divided into equal size pages. Read the points. Physical address space is divided into equal size frames. In paging, the frame size is equal to page size. काफी कुछ ज्यादा important point ये second point में लिखा गया है, ये काफी ज्यादा important है. When a process is created, look at this. When a process is created, paging will be applied on the process. A page table will be maintained in the main memory for a process. The base address of the page table will be stored in the process control block. अभी मैंने कहा था PCB. Base address, that is page table base register value. The number of entries in the page table is equal to number of pages in the logical address space. Each page table entry contains the frame number. Hence, the page table is also known as the address translation table. All the points which I told are at one place. There is no external fragmentation in paging. Internal fragmentation may exist in the last page. Last page में internal fragmentation हो सकता है, आ सकता है. ये diagram है, देखिएगा. Finally, you can say this as the algorithm. This is the algorithm of paging. Architecture, algorithm of paging. Architecture or algorithm of paging. So CPU generate logical address bifurcated into two parts, page number and offset. Using page number, we index into page number, get the frame number F, append the offset D, generate the address, physical weapon. ये है basic ideology of paging. We can take some simple questions based on paging जो अभी हमने देखा. चलिए start करेंगे. First question. You should try to work out question 1. Suppose imagine a system generate logical address of 25 bits. And the corresponding physical address of 21 bits. Let's say page size is 4 KB. ठीक है. Then question is, I want to know the following parameters. I want to know the following parameters. Number 1, what is the length of logical address space? Number 2, what is the size of physical address space? Number 3, what is the number of pages? These are pages. What is number of frames? M dash. M dash is number of frames. What is page number? What is frame number? What is page offset D? And I would also like to compute what is page table size approximated in bytes. Come on, boys and girls, I will give you a minute of time. Can you work out all these problems? Can you work out all these problems based on this given data set? Come on, do it. I'm trying to work out here. Please have a look. First of all, logical address space 2 power 25. तो क्या होगा ये 32 MB. Physical address space 2 power 21. क्या होगा 2 MB. What will be the number of pages? Number of pages will be 2 power 25 divided by page size. Page size कितना है 4 KB. Can I write 4 KB as 2 power 12? Yes. This is equal to 2 power 13, which is 8 kilo pages. There are 8K pages. How many frames I have? 2 power 21 divided by 2 power 12. So this is 2 power 9. There are 512 frames. 512 frames. Page number देखिएगा, number of pages 8K, so 13 bits. 13 bits. Frame number 9 bits. Page offset 12 bits. So that you can put the logical address format. You can put the logical address format. The logical address format, and let's say this is the physical address format. The logical address, this physical address. Logical address will have two parts, P and D. Physical address will have two parts, F and D. So what is the value of P? 13 bits. What is the value of D? 12 bits. What is the value of F? 9 bits. This is 12 bits. So this makes how much? 25. And this makes how much? 21. That's the correlation. Okay? Check all the values and see whether you have got the understanding or not. What is page table size? Page table size in memory in bytes will be number of pages capital N multiplied by entry size. What is E? E is page table entry size. Page table entry size approximated in bytes. So how many pages I have? I have 8K pages, 8K entries. And now entry size depends on frame number. Look at this. Entry size depends on frame number. So frame number is 9 bits. 9 bits को अगर आप bytes में store करने की कोशिश करो, roughly I need 2 bytes. Roughly. Right? So that's why I say approximated size of a page table into 2 bytes, which is equal to 16 kilobytes. You are not going to multiply 8K into 9 divided by 8. That is wrong. Because entry size generally is approximated in bytes, because along with frame number in page table entry you can contain other information. That's why I am taking to the nearest byte. That is the reason. So I am not going to multiply 8K into 9 divided by 8 because one byte is 8 bits. That is incorrect. तो ये होगा आंसर 16 किलोबाइट्स. ठीक है, चलिए और एक क्वेश्चन एक लेते हैं so that you can build up understanding. Second question. Consider a system using simple paging technique simple paging technique with system having 512 pages and 64 frames. 64 frames. If the length of logical address (1920 bits), then what is page size and the size of physical address space in bytes? Come on, work out this question. Work out this question. Bikram Pradhan, if you get a good rank within 200 or 250, then you stand a chance to get into IIT. Bikram Pradhan. IIT, old IITs में लाने के लिए you make sure that you are targeting a gate rank within 200, 250. Then sure shot, hopefully you should get within top level IITs. And as far as the question of Sidhu is concerned, I would like to tell that अगर आप preparation अभी start किए हो, then definitely you have ample amount of time. आपके पास काफी time है, 6 months का time है roughly, which is more than sufficient enough to crack gate and get a good score. 100% it is possible. And from my previous experiences where I used to teach earlier, I say that we have seen students cracking gate with just mere 2 months of crash batch preparation. We used to have crash batches, जहाँ पर we used to teach the students only for 45 to 60 days, and students have secured single digit rank, double digit rank and got into IITs. So beta Sidhu, I just wanted to say that 6 months is a good amount of preparation. बस आपको good amount of time for preparation, बस आपको एक अच्छी strategy बनानी होगी अपने से और एक dedicated तरीके से पढ़ना होगा, smart study करनी होगी, right? Minimum you have to spend around 10 to 12 hours a day with a systematic approach, then I'm very sure you can crack gate. Okay, definitely it is possible. तो चलिए इसका आंसर देखते हैं. What is the answer for this question? Consider a system using simple paging technique with system having 512 pages. Number of pages are 512. Number of frames m dash is equal to 64. Length of logical address is 20 bits. ठीक है? He's asking what is the page size and size of physical address space in bytes. तो सबसे पहले हम logical address format से जाएंगे. So imagine this is a logical address. By definition, logical address will have two parts, P and D. Length of logical address is given to be 20 bits. Look at this, these 20 bits. And number of pages are 512. So number of pages 512 हो तो we can find page number P. Page number is 9 bits. So this is 9 bits. So D कितना बनेगा? 11 bits. D will specify page offset. जब आपको page offset D पता हो तो page size determine कर सकते हो आप. So page size is equal to 2 power D is equal to 2 power 11 is equal to 2 kilobytes. That's right. Somebody has said already 2 kilobytes is the answer. Mohan, correct. Prashant also correct. So page size is 2 KB. And then he's asking what is the size of physical address space in bytes. So physical address size का format होना पड़ेगा. So let's draw the format of physical address space. तो physical address का format है two parts, F and D. Do we know F? Yes sir. Number of frames are 64. So therefore F is equal to 6. F is equal to 6. Frame number. Log of 64, 6. So these 6 bits. D from previous example 11. So this is how much? 17 bits. So we are saying that physical address is 17 bits. Physical address is 17 bits. So that implies physical address space कितना होगा आपका? Physical address space बनेगा 2 power 17, 128 kilobytes. 128 kilobytes. So that's the answer for the question. Okay. So next we are going to take up an issue of paging which is called performance of paging. So let's discuss this. performance of paging. जहां पर सबसे पहले बात होगी इम्पैक्ट ऑफ टाइम, impact of page table on time. See, as per the access, suppose if I say that the amount of time needed to access main memory, generally that is called main memory access time. So let us write it here. Main memory access time. We will write in short as MMAT. Suppose if I say main memory access time is given to be n units. This units can be in microsecond, can be in nanosecond. Access time का मतलब क्या है? The amount of time needed to read or write a word of memory. The amount of time needed to read or write a word of memory, that is called access time. So suppose if I say main memory access time is m units, then we know that in paging technique, अगर आप algorithm देखो paging का, the diagram which I said, so this page table is in main memory. So first we are accessing the page table when a process generates the address. So that will take a time of m. That will take a time of m. And then this addition of frame number and offset, that will take negligible time. इसके बाद we are referring again physical memory for my instruction or data with a time of m. So that means for every access I need a time of m plus m, which is equal to 2m. So that's what we say in paging technique, effective memory access time. Effective memory access time, we write in short EMAT. In paging technique become 2m, m plus m. M is for address translation, another m is for the final instruction data access, that is 2m. That means your program execution time will impact. Page table access की वजह से आपका program execution time बढ़ेगा. Program execution time बढ़ने से that will have an impact on throughput. So therefore, our objective is to reduce effective memory access time. So therefore, here I write the objective of this study is to reduce effective memory access time from 2m and bring it closer to m. So how can we do this? This can be done by using a technique, called, this can be done, let me see, the solution to this. Solution is to use a TLB, which is called translation Lookaside buffer. Generally, TLB is a associative cache or simply a cache memory which is faster access. So that TLB will contain some of the references of page table, meaning some of the previously resolved logical addresses and their corresponding physical addresses will be kept in TLB, so that we can reduce some of the accesses which are made to the page table and bring down the effective memory access time. This technique will be called paging with TLB. Look at this. This technique is called paging with TLB now. काफी ज़्यादा important है. Some questions were asked in earlier paper based on GATE, in the GATE exam based on this topic, paging with TLB. So translation Lookaside buffer is a hardware device implemented using associative registers. Associative cache means, let me write faster access memory. Faster access memory. So TLB is added to improve the timing performance of paging. The TLB access time will be very less compared to the main memory access time. So TLB contains frequently referred page numbers and their corresponding frame numbers. क्योंकि लॉजिकल एड्रेस और फिजिकल एड्रेस में जो कॉमन पार्ट है वो ऑफसेट है, तो वी डोंट बॉदर अबाउट ऑफसेट. सो कन्वर्जन इज ओनली कन्वर्टिंग पेज नंबर टू फ्रेम नंबर. So now with TLB, how does the architecture look like of paging? This is the paging algorithm now with TLB. So when I generate the address, the process running on CPU generate the address using page number, I index into TLB, where I can have TLB hit or TLB miss. TLB hit or TLB miss. मतलब जो पेज नंबर आप रेफर कर रहे हो, इट मे बी प्रेजेंट इन टीएलबी, इट मे नॉट बी प्रेजेंट. अगर वो प्रेजेंट हो टीएलबी में, दैट इवेंट इज कॉल्ड टीएलबी, जहां से हम फ्रेम नंबर लेके आएंगे एंड वी आर गोइंग अपेंड द फ्रेम नंबर टू द ऑफसेट डी, आई गेट फिजिकल एड्रेस. अगर टीएलबी मिस हो, दिस टीएलबी मिस, देन वी फॉलो ट्रेडिशनल पेजिंग, आई गेट द फ्रेम नंबर फ्रॉम पेज टेबल एंड अपेंड. So this is called paging with TLB. तो इससे परफॉर्मेंस कैसे इंप्रूव होगा, तो यहां पर हम लिख लेते हैं सम पॉइंट्स. सपोज इफ आई से मेन मेमोरी एक्सेस टाइम इज इक्वल टू m, TLB access time is equal to C. Time to read a word from TLB is C. Then TLB, अगर ये इसका परफॉर्मेंस डिपेंड करेगा हिट रेशियो पर, कितने हिट्स हुए हैं TLB में. सपोज इफ आई से TLB हिट रेशियो इज x%. TLB हिट रेशियो इज x%. दैट इज नंबर ऑफ हिट्स इन TLB. मानो अगर वी आर मेकिंग 100 रेफरेंसेस, सपोज इफ आई से 75 रेफरेंसेस आर फाउंड इन TLB, तो हिट रेशियो कितना बनेगा? 75 by 100, 75%, 0.75 TLB हिट रेशियो. तो बच्चों मिस रेशियो कितना बनेगा? TLB मिस रेशियो बनेगा 1 - x. अगर आपका हिट रेशियो 70% है तो मिस रेशियो 30% होगा. मिस रेशियो 30% होगा. तो in reference to this, the formula for effective memory access time now with TLB will be written as x hit ratio. Hit हुआ है TLB में, so therefore I get time. Then final access m for my content or instruction plus miss ratio 1 - x. TLB searching time we can add C plus 2m, or maybe this can be taken as time for updating the TLB, right? So C plus 2m. C plus 2m. This is the formula for effective memory access time. Effective memory access time. यहां पर आप देखो सेम थिंग. TLB access time is C, TLB hit ratio is x. Then the formula for effective memory access time is given by this. This TL1 TLB access, and these are one memory for actual page, and this TLB access 2m is one for page table, one memory time for actual page, memory read for page table, memory read for actual page. Actual page का मतलब you are accessing the instruction or data here, instruction or data. ठीक है. So this is the formula for TLB access time. Based on this we can take a simple problem, a simple question. See on board. Suppose, look at this data. Suppose memory access time is 100 nanoseconds. TLB access time is 20 nanoseconds. Suppose if I would have said page memory access time without TLB, page memory access time without TLB would have been 2m, which is equal to 200 nanoseconds. Now B, suppose if I using TLB, hit ratio is 90%, which is in the scale of 0 to 9 is 0.9, then what will effective memory access time become? So we can write 0.9 into 120, 20 plus 100, 120 plus 0.1 into 20 plus 200, 220. अगर आप इसे simplify करो, so this will come to be how much? 130 nanoseconds, I suppose. 0.9 into 120 plus 0.1 into 220. Is it not? (108 plus 22, 130). So therefore we can say that we have, when the hit ratio is high 90%, we have reduced effective memory access time from 200 to 130 nanoseconds. So we have achieved the objective. लेकिन इसीलिए इसके बजाय अगर आप यहां पर इसके बजाय if you would have said for example C, if hit ratio is 10%, just 10%, hit ratio is 10%, then what is effective memory access time? It will become 0.1 into 120 plus 0.9 into 220. So this will become 210 nanoseconds. It is increasing beyond 200 and beyond 200. It is increasing beyond 200. So from this example we can say that the deployment of TLB, in paging is justified if hit ratio is high. Otherwise, The purpose of TLB is defeated. Defeat हो जाएगा purpose. With hit ratio is 10%, then the purpose is defeated. It has even gone beyond 200, which is not at all desirable. So therefore, the usefulness of TLB is justified only when hit ratio is high. Otherwise, if the hit ratio is low, the purpose of TLB is totally defeated. So this is the organization of simple paging technique and its performance with regard to effective memory access time. So this is one complete topic on paging, which becomes the foundation or the base foundation for understanding of later other techniques like you have multi-level paging, you have inverted paging, paging with hashing, and then demand paging in the case of virtual memory. So this is the discussion with regard to simple paging technique. Okay, so that's what I have for today's session. Next session, either live or recorded, I will provide you the discussion on other forms of paging and the second non-contiguous allocation technique, which is called segmentation. जहां पर मैं बात करूंगा paging with hashing, inverted paging, segmentation, and if possible segmented paging. Then we'll cover up the virtual memory. Okay, so thank you so much. That's what for today's session. We'll meet in the next one. Okay.